Having spent 4 lectures on quantum mechanics and path integrals, now we get into quantum field theory. This is our course outline. We've gone through much of this. The first 4 lectures were about path integrals, imaginary time, instantons, dealing with functional determinants, and now we will talk about quantum field theory and the very simplest situation where quantum fields are involved. Now, this is going to be a very rich field. Tunneling in quantum field theory is going to bring up features that one does not see in particle mechanics. We will see that the existence of a derivative term is going to now introduce something that makes it impossible for the whole system to go from one state to another. In other words, tunneling of the entire field will not be possible. The applications of tunneling to various physical systems include spin glasses, electroweak vacuum, so the world that we live in, and this is going to actually take up most of our time. Next time, we shall talk about multiple vacua in QCD. I will not talk about superfluid helium or chemical reactions or the other applications because we will simply not have time. But here's how tunneling, how a quantum field actually can make a transition from one situation to another, from the false vacuum to the true vacuum. So by way of analogy, now, this is not quantum field theory. This is here we're considering super hot water. So let's say that T is something like 120 degrees centigrade or 150 degrees centigrade. So it's superheated vacuum. So it's superheated water. And this is what we will call the false vacuum. False vacuum because it wants to go into the vapor stage, which is the true vacuum, which is the true ground state of the theory. But you never see water suddenly burst and all of it convert into steam. What you see instead is the formation of bubbles. So tiny bubbles are formed, bigger bubbles are formed. Some of these bubbles, they stay, others evaporate, others then shrink and disappear. What's inside a bubble? Okay, so there is the pressure, the vapor pressure inside, and there's the pressure from the outside, plus there is a surface tension of the bubble. Now we are all familiar that if you have such a thing as a balloon, then the balloon is trying to contract because the bigger the surface area, the greater the force that wants to make it contract. There's pressure inside, there's pressure outside, and it's only when all of these balance out with each other that the bubble stays where it is. Otherwise, it'll either shrink or it'll expand. So this is going to be actually the kind of template that we will see for the instanton in quantum field theory. Let me just briefly mention spin glasses. So here you have spins which are randomly oriented here, here, here. And then for some reason, they can get into a lower energy state where all of them are aligned. So we go from the false vacuum where they are disorganized, they're pointing in different directions, into the true vacuum where they are all pointing in the same direction. And this configuration has got lower energy, and so this we will call the true vacuum. We will spend quite a lot of time on the Higgs field and the early universe. So the Higgs field, as you know, is a field that that's a scalar that's there all over space. It doesn't have electrical charge, but it has weak charge, and it's everywhere, and its expectation value is non-zero. This is the thing that gives masses to all the particles, the electron, the quarks, the W, the Z. All the masses come from interaction with the Higgs field. Now, the greater the magnitude of the Higgs field, the greater will be the masses. And if, for some reason, we are stuck here in the false vacuum where the Higgs field is less and the true vacuum has more, then the masses of the particles will change when we go from the false vacuum to the true vacuum. That would happen through the process of quantum tunneling. Now, we don't really know if we are in the false vacuum or not. So when the Big Bang happened, well, maybe after just a little while after that, we got into the true vacuum. If it's the true vacuum, then nothing will change. But it's also likely that it could be a false vacuum. How we know is a more difficult question than we will be able to answer now. That has to do with the question of effective potential, but we won't get into that now. However, the point here is that if the Higgs field is less here and more here, then the masses of the particles will change, which means that chemistry will change, which means that life will change. Maybe life won't be possible. And so that's the interesting thing that awaits us at the end of our calculation. We're going to be spending time working out the instanton of this theory. And just to give you a preview, so I haven't derived anything as yet, but the instanton in this quantum field theory will be a false vacuum outside, the true vacuum inside a bubble, and a transition layer where the two vacua merge into each other. And as we discussed in the quantum mechanical case, the instanton is very localized. You go from one vacuum, which we call minus A, to the other vacuum, which is plus A, with a very sharp transition. Okay, so without having derived this, let me tell you the result that we are going to get. We will be able to calculate the probability of tunneling out of the false vacuum into the true vacuum. This has to be per unit time, per unit volume of space. So you see, this makes sense. Suppose it's super hot water. The more water you have, the more bubbles you will form. But per unit volume of the water, that probability will be whatever it is. That probability will depend upon how much hotter that water is compared to the outside. There will be this exponential over here, b, which will turn out to be this integral, is the bounce action. And actually, this is telling you that the false vacuum cannot tunnel into the true vacuum all at once. It can't happen all over space. It has to happen through bubbles, because if this was constant, then you would have an infinite volume of space-time over here, and that would cost too much energy. So if B was okay, so if this V of phi B was constant, that is to say it was happening everywhere, then we would have e to the minus infinity. So not possible. All right, so here is the Higgs potential, actual potential. Here is the inverted potential, which we use in our instanton calculation. So you remember that for the case of the particle in a well, we made V go to minus V, and then we looked at how things slide down the peaks. In this case, what's going to happen is that the system is going to go from the false vacuum towards the true vacuum, and it'll bounce back. So looking over here, this is where the bounce happens. Here is where the bounce happens, and then it'll go back. Again, we haven't derived this yet. We're going to be deriving this towards the end of the lecture. In the approximation where the false vacuum and the true vacuum are separated by only a small difference at the level of epsilon, we are able to calculate exactly what A and B are, and they are very simple. This B is just proportional to the single instanton action to the fourth power divided by epsilon cubed. You see that if epsilon is small, B is large, which means you get smaller transition probability, and this S1 is related to the shape of the potential. So that's where we are going to go. That will be the final result. And now we have to begin talking about quantum field theory. Well, quantum field theory is very different from particle mechanics in the following sense. Normally, you think that a particle is at the position x at time t. But this is not how we are going to look at x and t. These are coordinates. There's no particle at x. There's no at time t. This is just a label. Instead, at this point, there lives a field. That field is phi. So, of course, this is the mathematical definition of a field. A field is just something which depends upon where you are at a particular time. That's what a field is. And the simplest case of a field is a scalar field. You can have vector fields, tensor fields, whatever. Okay. So here is the simplest Lagrangian density that you can write down for a field. This is what one calls the kinetic energy part, and this is the all this is the potential energy part. This is where the gradient of the field comes in, and this V of phi is without gradients. This is beginning field theory. Well, given a Lagrangian, you make the action by integrating over all space. Okay. As before, it's advantageous to go to imaginary time, so t goes to minus I tau. and the Lagrangian becomes the Euclidean Lagrangian. The only thing that changes, see over here, t is affected, not anything over here or here. So the sign over here changes. Now they're all of the same sign. And so in this S over here, we're going to have d tau, which is minus I. So dt is equal to minus I d tau, hence over here. And so when we calculate a transition probability from an initial to a final state, well, from the initial to the final, then with imaginary time, you're going to take the exponential of minus I over h bar into this action. So this action is made by taking this Lagrangian, and you see that the imaginary part has been made to disappear. So this is now well behaved instead of oscillatory. Of course, in going from here to here, you must now integrate over all possible fields that connect this to this. So when we are talking about paths, now the path means something more complicated than a simple line that connects point A to point B. Now you have to go from one field configuration to another field configuration. But the game is the same. S is a functional of phi. Okay, you perturb it a little bit. So delta phi is a functional which is a little bit different from phi, which means you can expand it in a functional Taylor series, first term being this, second term being this, and the third being this, and the rest, well, we can't handle them. We can only do Gaussian integrals, and after that we can do other things, but this is as far as we want to go to second order, and this is exactly what we did for particle mechanics as well. Okay, so nothing very new over here, at least formally. Of course, we're no longer dealing with x, we're dealing with phi, and phi has an infinite number of degrees of freedom, whereas x is 1 degree of freedom. But the game is the same, completely the same. The first term has to vanish. So you could say the principle of least action. And this is Newton's law in imaginary time, the equation of motion. And this is just what you would expect, d2 d tau squared plus del squared phi equals this. This b over here denotes the classical path. So this is classical, and now this stuff over here will give us the quantum corrections. Okay? A shorter way of writing this in the Einstein summation convention is d mu phi equals v prime. This is what you saw before. And now let's reflect a little bit upon boundary conditions. So the system is going to start from the false vacuum, move towards the true vacuum, but it doesn't have enough energy to jump over, so it goes back. Now, the boundary conditions that we're going to impose are that at t equal to minus t over 2 and at t equal to plus t over 2, we have the false vacuum. So we go from false vacuum towards the true vacuum. We don't reach it, but we go back, so we bounce. And this happens over all x. So this, remember that we're dealing not with a particle, but with a field. The field is defined everywhere in space. Okay, there's also a condition on the bounce velocity. So when it reaches the classical turning point, which is here, it has slowed down to zero speed. So the derivative with respect to time, and let's say that it reached here at time tau equal to 0, well, the bounce velocity is 0 at the classical turning point. However, remember one thing. This equation here doesn't care if you translate tau by tau plus something, tau plus 1, tau plus 3, whatever. And so this is time reversal invariant, which means that this tau equals 0 could be anywhere. Important point over here is that at large values of x, so that is to say at spatial infinity, the field has to be 0. So the bounce field has to be 0. The instanton field has to be, not 0, sorry. It has to be the false vacuum. Okay.
Professor?
Yeah.
So the implication of this discussion is we're saying the true vacuum is heavily localized.
No, the true vacuum is over all space. The false vacuum is over all space, but the instanton is very localized. So the instanton field, it goes from false to true over a very small distance. And so again, I come back to, okay, this is what you should keep in mind always. So the outside is the false vacuum. Inside is the true vacuum. In time, what will happen is that the true vacuum will become bigger and bigger, and the false vacuum will disappear throughout space. The transition between false and true, or true and false, this red thing over here, this is the thing that is very narrow. So the instanton is something that goes, that's why we call it an instant. It goes instantly from one vacuum to the other vacuum. Okay, so now let's get back. All right. So we need solutions to Newton's law, the equation of motion, which is this, with these boundary conditions. You know, the boundary conditions and the equation of motion are equally important. If you get one wrong, you have everything wrong. Okay, so we need to absorb this, that for the bound solution at time far in the past and far into the future, we have the false vacuum, and this is the speed being 0 at the classical turning point, and this is the field dropping off everywhere as you go to spatial infinity. Okay, now look at this. d2 d tau squared plus del squared. This is nothing but the Laplacian in 4 dimensions. Now the Laplacian in 4 dimensions can be written as an angular part, as a radial part and an angular part. But the angular part will not concern us. We will assume a spherical instanton in 4 dimensions, that is to say an O4 symmetric instanton, and you can ask why. The answer is that if you have variation, that variation costs you energy. And so the lowest energy situation is where you have spherical symmetry. I mean, this is just like in the case of the hydrogen atom, which is the lowest energy state. It's the S state. Always the S state is the lowest state. L equals 1, L equals 2, etc. They all have higher states, higher energies. And just to remind you, suppose we had 2 dimensions, the Laplacian in 2 dimensions, well, we would have d2 d rho squared plus 1 over rho. If we had 2 dimensions, we would have 2 over here. Sorry, I'm saying this wrong. In 2 dimensions, we would have 1. So the usual polar coordinates. In spherical coordinates, we would have a 2 over rho. That's what I'm sure you remember that from your study of the hydrogen atom. In 4 dimensions, we have 3. And okay, so rho squared is this thing. This is the radial distance in 4 dimensions. And you see, it's important that we go to imaginary time. Otherwise, you would have a minus over here. You wouldn't have tau squared, you would have minus t squared. Okay, so now that we have this simplification for the Laplacian, here is the equation of motion. So we have an ordinary differential equation instead of a partial differential equation. And this phi is a function of rho, which is this. Okay, now we can start calculating our action. So the action is the 4-dimensional integration over the Lagrangian. But you see, now this d4x in 4 dimensions, when there's spherical symmetry, is 2 pi squared rho cubed d rho. In 3 dimensions, it's 4 pi r squared dr. So it just directly follows from that times. So here we have rho cubed d rho. The Lagrangian is this. And now we recognize the fact that phi b just depends upon rho. So then this over here, you can easily write as this. Okay. So this is a 1-minute calculation. Just write d phi by d tau equal to d phi by dx into d tau, d phi by dx into dx by d tau, and then use this relationship over here to go from here to here. And of course, there's this thing over here. We have a second-order differential equation. We have to impose some constraint on it. That constraint is the boundary condition that d phi by d rho has to be 0. You see, that's necessary because when rho is 0, this would otherwise be infinite. Right, now we don't know whether there's a solution to the equation of motion. Just reminding you what the equation of motion is, it's this. Looking at this, it's not obvious that it has a solution. And now here's a way of I won't say it's cheating, but it's a way of getting intuition. Call phi b x rho t. Then this is x double dot plus 3 over t x dot equal to v prime, which depends upon t through x. Okay, now anyone who looks at this equation thinks back to the time when she or he studied differential equations for a harmonic oscillator. If this over here is the forcing term, if this over here was constant, that is, if 3 over t was a constant, then this would be the friction term. So it's a harmonic oscillator with a friction term, but the coefficient of friction becomes less and less as t becomes larger and larger. So we want to look at it from that point of view without compromising on the mathematics, subject to this boundary condition that at t equal to 0, the speed is 0, and after a long time, x of infinity is going to be 0. Okay, now does this equation have a solution? So a picture will help. Suppose that you start off rolling a ball from here. Okay, now if you start too close to the top over here, then this ball will roll down and it'll jump over the other side. Okay, remember that the final condition, the boundary condition is that x at infinity has to be equal to 0. So after a long time, this ball has to come to a stop right at this very point at the top. Okay, so you will overshoot if you're too high. You will undershoot if you are too low, because then what will happen is that it won't have enough energy, it'll go over here, and that won't fulfill the condition that it reach over here. So in one case you overshoot, in the other case you undershoot. So then there has to be some right value where you have exactly the right situation. So this is an argument of continuity. Okay, now let's get a little more rigorous. First of all, notice that if I take the derivative of this, half x dot squared minus v, well, that all you have to do is differentiate this, and you'll get minus 3 over t x dot squared. So I'm basically, I'm just rearranging it. Just do the differentiation. If you differentiate this, you get 2, which cancel this half, x double dot, and that's the thing over here, etc.
Or you could start backwards, shift the potential in the friction term elsewhere, and then realize you can take the time derivative common.
Yeah, so it's just a simple identity. Okay, now, suppose the ball is initially at t equal to 0 at some value of x naught, which is bigger than a, so here, and it passes by this point a at some finite time t naught. Then what's the energy loss going to be? The integral from t0 to tf of dx by dt. Okay, that's so that's the frictional term, 3 over t dx by dt. And you see that d by dt is equal to this. So all I'm doing is basically integrating the energy loss over time. Now look at this integral. T is always bigger than t naught and less than tf, which means that this integral is less than 3 over T naught. We can take this T outside, and we have this integral over here, dt dx by dt. Okay, forget the absolute value over here. This is, oh, just keep it there for a while, okay, T naught to Tf, which is here. And if this absolute sign was not there, this would just be, from the fundamental theorem of calculus, what's over here minus what's over here. So x at the position Tf minus x at the position T naught, which is A. Now this is saying that you can forget about the frictional term over here, provided that the starting time and the ending time are far apart from each other. That's because the friction goes down with time. Okay, so that will enable us to solve for the instanton. Here I've just reminded you of what we did in the case of particle mechanics. So I've just repeated the slide from the previous one. So you start with high initial friction, and so it takes a long time to get to the position here. And then, because it's taken a long time, the friction has gone down, which means now it is frictionless, and we can do our analysis as I had shown you earlier. What's the difference with field theory? Not very much. Here I've added a potential term. Here I've also added a potential term. Instead of x, I have phi. And this phi is not phi at x, phi over all space. It's the vacuum. So it's over all space. Okay, this is a symmetric vacuum. And as one example, you could take this. We don't have to, but it'll make things a little easier to understand. Okay, so just to remind you once again that phi is a function of t and x, which becomes tau and x, which becomes phi of rho in the case of spherical symmetry in 4 dimensions. But of course, we have an infinite number of degrees of freedom. And so here is something that particle quantum mechanics just does not have. It has, the field theory has the gradient term, which gives us this extra kinetic energy density. And hence, you would need an infinite amount of energy to change phi everywhere, because we have to integrate over all spatial x. Okay, so let's start solving the equation of motion. That equation of motion is here. d2 phi d rho squared is equal to this. And now, if you integrate that, you get d rho is equal to this. But now integrate both sides, and you get rho is the integral over phi of the potential, square root of 2 times the potential. At this point, you can say, oh, I'm going to expand V about phi equals 0. Well, we know that V, the symmetric part, has to be, its value has been chosen to be 0. So you see, just like here, the phi is 0, and here the phi is 0. It's at a maximum, and so there's no derivative. The only thing that remains is the second derivative, and omega by definition is the second derivative. So Vs of phi is this, which means that I can just integrate this. D phi over phi is log of phi. And that says that phi goes as either e to the minus omega rho or e to the plus omega rho. And remember that the translational invariance in time means that we can make rho go to rho minus rho naught. There's no rho naught which is fixed by the equation of motion, so we can make it change as we want. And so the solution to this, as in the case of the particle instanton, is just this. Phi of rho is equal to this. And here is the grand solution for the O4 instanton. There's almost no work that we had to do. All the work was done doing particle mechanics. What?
Oh, I'm saying it's pretty much identical to what we
Yes. Okay, so in fact, we can simplify this. We can say that this term can be dropped and this can be dropped for large enough omega. And the instanton, so phi as a function of rho goes from one value to the other value. So from the false vacuum to the true vacuum, the instanton instantly goes between one and the other. So it's like a domain wall. Okay, but one thing we haven't decided yet is what is the value of rho naught. See, the instanton is located at rho naught. But where is rho naught? Is it, well, we have to find out where that is. And now, we're going to do that by using the principle that the action must be minimized. So earlier we had used the principle that the action must be minimized, but we had not included epsilon in that. Now we are going to include the fact that there is a slight asymmetry. This epsilon over here is not zero. So one vacuum, the true vacuum, is a little bit below the false vacuum. Epsilon is very, very small. Now what we would like to do is calculate this action. And it's got the usual, well, it's got the kinetic energy and the potential energy piece in it, and it's got the asymmetric potential energy piece as well now. You see that if phi b is equal to A, like over here, then this will be 0. If phi b is equal to minus A, this will be minus epsilon. So it's minus, so this term over here is minus epsilon on this side, 0 on this side. And what it is over here doesn't really matter, because here we have a huge volume of space to integrate over, and similarly over here. Whereas from here to here is very, very thin. Remember that the boundary of the instanton is very, very thin. So it's like the bubble in the superheated water. The wall is very, very thin. So the thinness of that wall is the thinness of this instanton here. Okay, so now we have to do this integral, and now this integral can be divided up into three parts. You'll go from 0 to just a little bit of, you'll stop a little bit before the wall, then you'll integrate through the wall, and then you'll integrate after the wall. So now we will do all three integrals. Well, the first integral, so you see, rho is going from 0 to just before the wall. And we have this rho cubed, which came from the Jacobian, from the fact that we had the volume in four-dimensional space was 4 pi squared rho cubed. On this side, what's inside over here is just minus epsilon. Why? Because you can see that phi is constant over here, hence this is 0. And this over here is minus epsilon. Okay, so we have this over here. Then we integrate across the instanton, so where it is rapidly changing from one value to the other. So we need to do this integral. And then here, this term, well, phi b is equal to a, so this is equal to 0, so there's nothing to integrate over here. Now this part is easy. Anyone can integrate rho cubed, it's rho to the 4 over 4. And that's why you get this over here. This part over here, okay, now this is just, I can extend this from, I can take the lower limit over here to be minus infinity and this to be plus infinity. But basically, I'm integrating from here, this place here, to this place here. And that's where all the energy of the instanton is concentrated. So I get the action here, which is, yeah, I put minus infinity and plus infinity because that's easy, makes the integration easy to do. But it's a very good approximation. And so this part over here, we've done this before. That's just square root of 2 times v. Okay, so look over here. This epsilon is positive, right? We've said that before. This part is decreasing with rho naught to the power 4. This is increasing with rho naught to the 3. When will the action be minimum? Well, you differentiate with respect to rho naught. Rho naught is the position of the instanton. So you fix the position of the instanton by minimizing the action. And in this way, you get rho naught, the position of the instanton is this, 3s1 over epsilon. And if you put rho naught equal to this, put it back in s, well then s works out to this value over here. So that's a good achievement. Finally, and I'm getting close to the end, let's consider an observer who is moving with the wall of the instanton. At the time of formation, the instanton is so think of it this way. In the water, this bubble has been created. The bubble has been created at rest. And now that bubble is expanding spherically, symmetrically. At the time of formation, there is no kinetic energy and the bubble radius is rho naught. The energy per unit area of the bubble is this. What is it? Well, per unit area means we divide by 4 pi r squared, 4 pi rho naught squared. So remember, this is at tau equal to 0 that the instanton was created, which means that rho squared is equal to the magnitude of x squared. Okay, so we have to calculate this over here, which is easily done because d3x, we're in 3-dimensional space. The bubble is in three-dimensional space. It's 4 pi r squared dr. And there's this thing over here. But you see, this bubble is so thin that why do I need to integrate? Why can I not simply say that r is a constant equal to rho naught? So I pull this outside and I get this. But this is exactly the action for a single instanton. So the single instanton action and the instanton energy are equal. And now remember that the instanton is actually in 4 dimensions. So how fast does the wall move? Well, this rho naught is a constant. We fixed it. You just saw what rho 0 is equal to. It's fixed. It doesn't change with time. So rho naught squared is equal to this. Now we're moving back into real time, from imaginary time to real time. And I've put the speed of light over here now to make the dimensions consistent. Okay, so we have this bubble that is expanding into space. We know from special relativity that energy transforms as the time component of a 4 vector. So we have to multiply by gamma, where gamma is the speed at which the bubble is actually expanding. You can see it's moving fast because look, this over here is constant. And this means that R will be like CT. So it start at t equal to very small. The speed will be 0, but then it'll be moving faster and faster, expanding at the speed of light, near the speed of light. Well, let's be a little more careful and just differentiate this. So look at this over here. Differentiate both sides with respect to time. Then the velocity of the wall will be equal to c squared t over r. R is equal to square root of this. And now gamma, put in gamma over here. So this is r over rho naught. Okay, that means that the energy is, now you just do this simple calculation that you put gamma, so this gamma over here, r over rho naught, the multiply by the surface of the bubble, which is 4 pi r squared, and this is the energy per unit area, which is equal to the action of the single instanton S1. Put that in, and we get this amazingly simple result that the energy now is increasing with the volume of the bubble. It makes a lot of sense. If you have this bubble inside water, superheated water, the bigger the bubble, the bigger its volume, the bigger the energy of the bubble. Now the bubble is, you can see from here, V is equal to C, Ct over this. And as T becomes large, you can forget about that. The bubble is expanding at the speed of light with only the true vacuum inside. So the steam is taking over the water. All the energy from the false vacuum has gone into the wall. And that's very interesting. It's saying that there's no see, all the energy has been used up, and none is lying around creating useless particles. So it's a smooth transition. This is the O4 instanton that we've that we've just now completed and discussed. So this thing over here, the true vacuum is becoming bigger and bigger until it takes over the universe. Now this little bubble is expanding at the speed of light, so you can't get out of its way. And if it happens, then you won't know what hit you. Okay, and so that's the end over there. These are some references that I have on this, and this book is very good. See if you can get it. Okay, so now we've come to this very grim conclusion that if the universe is going to go from the false to the true vacuum, there's absolutely nothing you can do to get out of the way or to make preparations, because that bubble is coming at you at the speed of light. Okay, good. We're done on that. Questions?
Could you please go back to the slide where you have written this energy loss?
Huh.
No, the previous one, the first one. A little, no, we have to go back again, yes. Because this is one more slide, yes. Yeah, this one, yeah.
Huh.
Is it energy loss is 3 by t dx by dt or dx by dt squared?
Okay, so this over here is the energy, and the rate of change of this is equal to this. So what is it that we should? So this over here is the rate of change of energy. The energy will actually be 3 over t times dx by dt. Yeah.
So I have a question. So this state is decaying from some higher energy to lower energy. So shouldn't we expect some energy to be released or something like that?
So the energy, where has the energy gone? The energy is in the wall, and the wall. So of course, energy will be conserved, but it's there in the wall, and since the universe is infinite, that wall is carrying the energy away with it. And it's carrying it at the speed of light. Yeah, so the total energy has not been lost. Whatever difference there is between the false and the true vacuum energies is there. It's just in the wall, but you're not going to see it because it's rushing away at the speed of light.
Okay.
Sir, the bubble is expanding because of Instanton bouncing. Like, why is it expanding? Like,
Why? Okay, so it's not expanding in 4 dimensions, it's expanding in 3 dimensions. So I ask you to look over here, okay? This rho naught is a constant. Let's say it is 3 or 5 or whatever in some units. However, R has to increase with time to keep this constant. So R squared is equal to C squared T squared plus rho naught squared. So it's not expanding in 4 dimensions, it's expanding in our world, in our 3-dimensional world.
You have written that consider an observer who is moving with the wall, and your wall is moving with the speed of light. So
Yeah, but it's not moving at the speed of light.
Approximately.
You see that dr by dt is equal to this c into this thing. So it's approaching the speed of light.
Oh.
Yeah.
What are the odds, though, that we're in a false vacuum?
What's that?
What are the odds that we're in a false vacuum? We have this grim result, but what can we say about our own universe?
Okay, so everything depends on the shape of the potential. It may be that we are living in the true vacuum, that the next bump in potential, if there is one, will lie higher than this. So maybe we are in the true one. How do you decide this on the basis of quantum field theory? Obviously, there can't be any observational evidence. So what people do is they take the standard model and they compute the effective potential. Now, the effective potential is a correction to the basic theory that we did just today. And the effective potential then gives you corrections which go beyond the quadratic approximation that we have used. From that, they're able to use certain things like the mass of the top quark, the mass of the Higgs, to compute V of phi. And the V of phi that they find as of a couple of years ago is just at the borderline, that maybe we are safe and maybe we are not. So there's some room for error over there. But you see, the interesting thing is that here we said, give us a potential. So this was Coleman's calculation. He said, suppose there is a true vacuum which is a little bit lower than the vacuum that we are living in. Then he did this calculation. Okay, but where did that potential come from? He didn't know. But now people are able to put the full standard model together. So you see, what we've done is we've used only a tiny part of the standard model.
The standard model is much larger.
Yeah, it's got actual particles in it. It's got quarks and gluons and leptons and everything else. And so when you do a full standard model calculation, which is much more complicated than what we've done, then they are able to come up with a V of phi. And that V of phi is neither grounds for fear nor for optimism. Okay, so good.